You'll be able to find this video on YouTube. I'm trying to be very disciplined and make sure that every lecture gets recorded. Okay, so here's the structure of our course. Today, this is the first lecture, and we're going to focus on the big picture. That is, we're going to take a look at everything that's covered in the class and do it in 2 hours. I have to skip a lot of details. And then, as I said, we're gonna go over all this material multiple times so that you're comfortable with the concepts and how we got them. The next week, we'll talk about the early universe and the very important experiment that gave us a description of the microwave background that's a leftover from the Big Bang. And so here's some details about that. Third lecture will be about expansion of the universe. And here's some details. The fourth lecture will be about the dark universe. You perhaps heard about dark energy and dark matter. These are mysterious properties of the universe only recently discovered in the last 25 years in the case of dark energy. So that'll be covered in lecture 4. Lecture 5, we're going to go into some of the technologies used to develop the data that we have and gave us the ability to understand the structure and dynamics of the universe. And the last lecture, lecture number 6, is a discussion of the recent products from the James Webb Space Telescope and other resources that have attempted to answer questions raised in all the earlier cosmology research, but questions still remain, and they're profound, deep issues that we have to talk about. So that'll be in lecture 6. I just want to alert you that you'll have access to these charts. In some cases, you'll find a line like this, and below it, there'll be details, some text to help explain the content of the chart. So don't overlook looking at that material. If you have questions, put them in the chat while I'm talking. I'll have to make a decision. For example, when we get to our break, after about an hour, we'll have a break, and I'll take a quick look at the chat, and if it's appropriate, I'll try to answer questions in the second session of this presentation. But put your stuff in the chat. In case I don't get a chance to answer your question, I'll have your question and I'll share your question and the answer with the entire class. You can also send me questions via email, and you see my email down here at the bottom of the page. If you send me a question, I'm not going to answer it just to you. I'm going to answer it for the entire class. So let's make sure that everybody understands your question and the answer will be shared with everyone. And CSU is going to manage your access to the lecture notes, and through them, I will share the link to the YouTube video, such as the one I'm recording right now. Some of the lectures have so much artwork that I can't share the entire thing. So I have to resort to a PDF format, and it just depends on how much I can squeeze onto the server. And we've already talked about YouTube. Now we have the issue here of a lot of people like to have the notes ahead of time. And I generally have avoided that because your questions and comments may cause me to alter the chart package while I'm presenting. And so I want to wait until after the session is over and that I've read your questions before I provide a copy of the notes. It doesn't satisfy everybody, but it has worked out best for me in the many times I've taught this class. Now this zigzag here is is there to remind you that cosmology is the study of the entire universe. It relies on many sciences, physics, chemistry, mathematics, and so forth. And so the ideas that have evolved, the ones we embrace today, are the result of the typical meandering path of scientific progress. In a lot of cases, progress occurs and then we have to backtrack. So that's why I'm going to cover every topic that I introduce to you multiple times so that you can see that there is a path forward. It's just challenging to present it all chronologically, for example. So I'm going to explain what we know about the universe and those various sciences that make up, when added together, a coherent view of cosmology. And we'll talk about technologies, telescopes of various kinds, other kinds of instruments and that we rely on. And here's an example, by the way, of, on the left, a picture of galaxy. I've forgotten just which one it is yet, but this one, the one on the left here, is done by the James Webb Space Telescope. And on the right, this is from Hubble. And I should point out right now, you can always tell Hubble images. If you look at a bright object in a Hubble image, it will have crossed lines. I'll explain in a few weeks what that comes from. It has to do with properties of the telescope design. And this is the property you get from James Webb. And let's look at this real quick. This is an animated version of that picture. So if you click on this, you can do your own view of this. Sliding this line back and forth lets you compare the performance of, in this case, I'm showing the Hubble result, in this case, the James Webb result. And we'll talk about why that's an important improvement, not just in resolution, but also in the way the telescope gathers information. So here's a key page. I'm going to summarize this and let you read it in more detail on your own. But it's obvious the universe is huge and complex. And we might wonder, how can we make any progress understanding something this immense, since we can't go to the places in the universe we'd like to study in detail? And yet, we understand a great deal. We have, even better, we have multiple independent ways to confirm the results we get from our observations. We're not done by any means, but the consensus for our understanding of the universe relies on using independent confirmation as we do in other sciences. It doesn't help to have a single scientist or observation tell us something. We need confirmation by having others look at the same topic. So I'll ask you to read this so we can get to the beginning of the lecture, which hasn't really occurred yet. And here's some references you can use. These are these typical things that you find if the Earth was the size of a grain of couscous, which is a few millimeters, the sun would be the size of a ping pong ball 15 feet away. These kinds of things maybe help you have a sense of the scale. And we also, because the universe and its properties is to a large degree, is dictated by the behavior of the smallest particles, subatomic particles. It's good that you know the terminology for things smaller than micro, nano, pico. We'll go over these things in more detail, but it is important to know that the smallest things influence how the entire universe has evolved. So here are my definitions for key terms, such as a comparison between astronomy, an ancient art, dates back thousands of years, and the modern view of the sky, astrophysics, because we now have the tools that we'll go into in a lot of detail, how to understand what goes on in stars and galaxies. Cosmology relates to the structure and dynamics of the entire universe. And I've already talked about the fact that the word modern is important. We're not going to cover ancient ideas about the structure of the universe that involved stacks of turtles, that there are turtles all the way down. You can look that up if you care to. And we have some other terms we're going to go over many times. So now, finally, we're at the beginning of the science we're going to talk about today. Here's an image taken by the Hubble Space Telescope of a supernova that occurred in 1987. And we see this expanding ring of gas and dust being illuminated by the radiation and high energy particles emitted from the center of this explosion of a star. And we can compare that to this same image taken by James Webb Space Telescope. Different kinds of details are revealed when you compare these two. So here's the big picture of the universe in one slide. If you're doing chemistry, you talk about atoms and molecules. If you're talking about the solar system, you talk about planets and asteroids and stuff. In cosmology, the unit of measure is galaxies. Keep that in mind. We'll be spending a lot of time talking about galaxies. Most of what we have gathered in understanding galaxies and groups of galaxies in the past has come from light. And when I say light, I'm including the light humans are sensitive to, and other forms of electromagnetic radiation, infrared, X-ray, and so forth. That's changing. We have new technology now that we'll talk about in detail. What we know from collecting light from galaxies is there are about 100 billion stars in a typical galaxy, and the universe appears to contain about 100 billion galaxies. So this is a staggeringly large number of stars. Even the number of galaxies is stupendous. It's astronomical. So here's what we've learned from looking at galaxies. The universe is expanding. This was a surprise in the 1920s, so 100 years ago. We'll talk about the history of that. The universe is expanding, and in around 1998, we discovered that its rate of expansion is increasing at an increasing rate. That'll be an important part of what we talk about. Most of the matter and energy in the universe is unexplained. The startling thing is that of all the forms of energy in the universe, only a little less than 5% is energy in the form of atoms. And almost all of this is in gas, hydrogen and helium gas, floating around between the galaxies. A tiny, tiny fraction of the energy in the universe is in the form of atoms that have collected in stars and planets. But the important thing to know is 95% of the universe is unexplained, and we'll get into some of that today. We have learned also from our observations that the geometry of the universe is flat. It's the same sense of flatness that we learned in the 9th grade or the 8th grade, whenever you took plane geometry. And there's a difference between the geometry of the universe and the shape of the universe. And I'm going to show you the difference very explicitly. We also know that our observable universe has existed for nearly 14 billion years. Any other observer in the universe far away has a different view. They have a different observable universe, but it's lasted this long. The universe is much larger than this number times the speed of light. I'll explain that. In fact, I do it right here. If you look to your left and you look as far as you can see using scientific instruments, the most distant objects are about 45 billion light years away. And if you look to your right, objects are the same distance apart. So we say that the scale of the observable universe is at about 90 billion light years. And you're going to have to become comfortable with this as a measure of distance. Light year, the distance light travels in a year, is a stupendously large number. But everything we're talking about in cosmology is so huge, we can't use miles or kilometers or measures of that type. We have to talk in terms of light years or millions of light years. So in any case, the scale of the universe is measured in numbers this size. And I'll explain all this. We do have a model of the early universe, and it is consistent with what we observe out in among these galaxies that we look at, that the predictions we have that we derive from our understanding of nuclear physics is consistent with an early universe, this age, with this fraction of the energy in the universe invested in atoms. And this model compares well with what we see in the galaxies. We can look at the chemistry of galaxies and we see agreement between our models of the early universe and what we see today. Now, I mentioned for almost the entire history of modern cosmology, we've been using light to characterize the properties of the universe, but we have new observatory techniques. We have gravitational waves. They've been in the news for about the last 10 years. We have particle physics and new insights related to how subatomic particles are involved in the evolution of the universe. And we have this very important resource, the cosmic microwave background, that has revealed an enormous amount of information about the structure and evolution of the universe. And we have lots more to learn. So if you want to see a fun video that dates back roughly 50 years, you can click on this and you'll see a quick tour of the universe and a more modern version if you click on this. So anything you see that has this structure blue with underline means it's a hot link that you can follow. So now let's talk about a number of features of the universe that are up until the 1980s were a complete surprise. The universe is expanding. And this is always a conceptual challenge, and we have to overcome our concept of what it means to expand something. And the easiest way to do it, even the way that the professionals do this, is to imagine a balloon that gets bigger. A balloon has no edge, and we believe the universe has no edge, just as there is no edge to a sphere. We also find that the expansion of the universe means that objects more distant from us speed away faster in our expanding universe than nearby objects. Remember, when I talk about objects, I'm talking about galaxies or clusters of galaxies. A galaxy cluster might contain roughly 100 to a few thousand galaxies that are bound together by gravity. We have a relationship, for example, with the Andromeda galaxy. The 4 or 5 billion years in the future, the Andromeda galaxy, our nearest neighboring galaxy, will pass through the Milky Way. They will pass through each other. They happen to be so close that they are gravitationally bound. But when you look at large-scale properties of the universe, everything is receding from everything else. And you might wonder, since the universe is expanding, does that mean that Earth is getting bigger or we're getting bigger? And the answer is no. In the case of astronomical collections like the solar system, Gravity assures that the Earth and its distance from the sun and the other planets, that's not changing because of the expansion of the universe. Galaxies even don't change size because of expansion of the universe. Galaxies get farther apart because the space between the galaxies is expanding. But the galaxies themselves are bound together by gravity, even though the universe itself is expanding. And atoms don't even notice this expansion. So here's the way to think about it. Here's a sphere, a simple sphere, and on it I've placed some galaxies. Far in the future, that spherical structure, if it's anything like our universe, the sphere will get bigger, but the galaxies will not. I've made these galaxies the same size on purpose. They get farther apart, but the galaxies themselves do not increase in size. So this is our first introduction to expansion of the universe. We'll be going over this frequently, and hopefully by the end of even today, you'll be comfortable with this concept of expansion of the universe. Not only, this is our second surprise, not only is the universe expanding, its rate of expansion is increasing and has been since the early, about 7 billion years ago. Remember, I said the universe is about 14 billion years since the Big Bang that we acknowledge as the beginning of our observable universe. And for roughly the first half of that 14 billion years, there was expansion, but the rate was slowing. And this is due to the gravitational attraction between the components in the universe. The early galaxies were interacting gravitationally, but there was something else going on that I'm going to show you here in a second. And that other thing is something called dark energy. This is a property of the universe not discovered until the late 1990s, and it was a complete shock. Researchers who were trying to measure the slowing of the expansion rate were shocked to find that the slowing was in fact negative. That is, the rate of expansion of the universe was increasing. So let's look at this curve. We're going to see a lot of graphs in this class, so we might as well get used to this. This is time since the Big Bang in billions of years. This is G years. We're using the European abbreviation for billion as a capital G. So in the very early universe, the expansion rate was very large, but was gradually decreasing because the matter in the universe was attracted, all that matter was attracted to each other by gravity. And the universe was small enough that that attraction was significant and it was slowing the expansion rate. But in the early universe, this dark energy was present. It just had very little influence. And that's this green dotted line. That's the dark energy influence. And right here, about 7.5 billion years ago, the influence of dark energy became prominent and overwhelmed the gravitational attraction. So the gravitational slowing is still there. It's just not important anymore. And we now are on a upward trajectory of expansion rate. And this, we think, will continue for the rest of the history of the universe, that the expansion rate will continue to grow. And that has some consequences for how the universe is going to evolve. Now, surprise number 3, I already mentioned, the universe has a geometry. It's flat. So that means if you go out into the universe with various measuring tools and measure a triangle, draw a triangle out in the universe, the sum of the angles in that triangle is 180 degrees. This is a property of a flat geometry. Let's look at what I'm talking about here. So here's that triangle. You can draw it out there in space and make careful measurements of these angles, and you will get 180 degrees. If the universe had curvature, a curved geometry, you would not get 180. And we'll talk about this repeatedly. A similar experiment you could do would be to draw a giant circle, get a piece of string and hook it to a rocket that is out there, and you're out here as an astronaut, and you measure the circumference of a circle. If the geometry is flat, the circumference is 2 pi times that radius. In other geometries, you would not get that answer. And we've done all sorts of experiments using light from galaxies and stars to confirm these kind of properties. A straight line is the shortest distance between 2 points in such a geometry. Parallel lines never cross, and so forth. And I already said there's a difference between geometry and shape. Let me illustrate it to you. This is one of my wife's sewing patterns, has straight lines and triangles and so forth. This is flat. It has a geometric flat property, but it's also has a flat shape. You can pin this thing to a flat work surface, and the flatness here, both in terms of geometry and shape. But if you look at the packaging that this form came from, it's rolled up. And this is clearly not a flat shape. It's a tubular shape, and yet it is a flat geometry. If you look right here, you'll see properties of triangles that satisfy all these requirements. If you go look closely, you'll find that this rolled up version of this flat geometry doesn't have a flat shape, but it still has a flat geometry. And later in well, actually, you see a link here that I've added that you can read yourself. And it's the issue of what is the shape of the universe? And the answer is we don't know. We know it has a flat geometry, but not a flat shape. So let's, and I also provided this hot link. You can see some examples of various kinds of shapes that have been considered. But right now, we don't know the shape, but it's an active area of research. The next surprise is 99% of the atomic matter in the universe is either hydrogen or helium gas floating around between the galaxies, or not in stars or planets within a galaxy. And what's more, we have this as our first example of our understanding of the Big Bang synthesis of various elements in the periodic table. Of course, you recognize this periodic table from when you took chemistry or physics. And this is color-coded to indicate what atomic materials were formed in the Big Bang. And the intense pressure and energy that existed in the very early universe, and we get hydrogen, helium, and this bit of lithium. Lithium is a metal. And then you see other sources of various kinds of atoms that we find here on Earth, in the solar system, and out there in the cosmos. And we find that exploding massive stars, you see as this yellow color, a large fraction of what's out there is produced in exploding massive stars. We have a little bit here. These are human. This gray color provides it. The scale of human development of temporary exotic atoms that don't exist in nature, that come from reactors or exploding bombs. But you can see here, we now have good agreement between this periodic table and its indication of where these various elements came from. Like xenon here results from low mass stars exploding and neutron stars merging. And in fact, quite a few of these atomic species rely on neutron stars. We'll talk about what neutron stars are off and on during this class. So we have good agreement between the numbers we measure in galaxies. We'll talk about how we make those estimations and what we know about nuclear physics and the formation of atoms. Here's surprise number 5. Perhaps this should be number 1 because it's this shocking result that atomic matter, of which we are made and stars and planets, represents only 5% of the energy in the universe. Now, what are the other types of energy? So here are the stars, this green slice, and here's the free gas that floats around in and between galaxies. That's that slice. And then there's other smaller species, exotic particles called neutrinos and so forth. Everything we see in the physical universe is in this slice, and it represents 5% of the universe. Dark energy, I've already discussed. There's different ways to measure it, but the typical result is that 70% of the energy in the universe is dark energy, and that fraction is growing because a bigger universe has more dark energy. At the same time, we have something called dark matter. We do not understand this. We can describe its behavior, but why it exists and what it's made of has not been explained. There's a lot of active research in this area. So we end up with a huge fraction, 95% of the universe is unexplained. And we'll get into all that. And this is new, particularly this huge slice here. If you read books written for the general public about astronomy before 1995, you might as well set fire to that book because it didn't know there was even an issue about why the universe is expanding at the rate it is. Because before 1998, no one knew about this huge influence, dark energy. So we'll be in that quite a bit. Surprise 6, the universe is vastly bigger than the part we can see. We have an observable universe where the most distant objects are, as I already talked about this, most distant objects are about 45 billion light years away from us at the current time. And so if you look to your left and you look to your right, you get an idea. The scale of the observable universe is about 90 billion light years. But the universe is even bigger than that. Because of the expansion of the universe, the objects we can see are the ones that are receding from us at the speed of light or slightly larger. We'll talk about that. The universe is filled with objects that are receding from us even faster than that. So this is the estimate for the most distant objects we will never see. And we're measuring this in not billions of light years, but trillions of light years. So we are involved in an expanding universe. And let's go for a second, go back to that spherical analog that I provided, where you have galaxies pinned onto a two-dimensional sphere. For example, a balloon, and from a geometric point of view, is a two-dimensional sphere. Meaning it only takes 2 dimensions to describe any point on that sphere. Latitude and longitude are what we use to define a point on the surface of Earth. We don't need more dimensions than that. So that's called a two-sphere. And I've already mentioned, we don't know the shape of the universe, but it could be the universe is a 3-sphere. That is, it has a dimensionality that we do not experience. And that's the increasing radius of that 3-sphere that is descriptive of the expansion of our world. You can imagine a sphere covered with little creatures that are two-dimensional. Perhaps we'll call them ants. So there's ants walking on this hypothetical 2-sphere. And if that sphere gets bigger, the ants get farther apart. And what's more, the ants can explore that sphere. They can only go forward, backward, left, and right. They can explore their universe, this 2-sphere that I've conjured up. They will never find an edge. If they go long enough in one direction at high enough speed, they'll come back to where they started. And it's possible that we are living in a spherical universe of a higher dimensionality than the one we're aware of. And this is mind-bending, I know, but it's the same thing that professionals talk about when they talk to each other. They have two ways of describing the expansion of the universe. They can talk about ants walking on a surface of a sphere, or they can do math. Because when you do the math of higher dimensional spheres, you can just set aside your worry about what does that actually mean. The mathematics provides you with the tools for doing that kind of mental exploration. So I know these are challenging topics, but we are going to dig into them as much as we can. And here's an example of the structure of the universe. It's not the universe, of two galaxies after 4.7 billion years of evolution. I just add this to just remind us we're dealing with huge complex objects like galaxies that have trillions of stars, most confined to this center where it's bright like this. And all these little dots in the background are just like this, but so far away that we can't see these details. It's also true, as I cover here in this last point, that because of the expansion of the universe, assuming that it continues as it has been for the last 7 billion years, an astronomer in the far future will not be able to see anything but the stars of the Milky Way, that's our galaxy, and the Andromeda galaxy that will collide with us in a few billion years. All the other galaxies will have been carried so far away from us that they will be invisible. And the ability of astronomers in the distant future to tease out what we know now will be completely lost, because they will not see all these wonderful complex galaxies and their dynamics. They will all disappear. They will just see nearby stars. So we'll get into that some more. But I congratulate you for deciding to take this class, because in the far distant future, we won't know, the astronomers of that time will not know how to get this information. Let's keep going. We are really star stuff. This was an idea introduced by Carl Sagan when he did the Cosmos series almost 50 years ago. 10% of your body is made of stuff created in the Big Bang, and the rest comes from exploding stars. Here's a picture of a supernova event that occurred some time ago. Somewhere down here is the remnant, probably a neutron star that survived the explosion of the star, and it blew out all this debris, different kinds of atoms that we showed on the periodic table, and that's just a cloud of stuff that will someday far in the future become part of the new galaxy and a new planetary structure, perhaps. So here's the way to look at this. This is the differentiation between different kinds of atomic species. Lots of oxygen, carbon, hydrogen, and nitrogen, and then a scattering of other stuff. And here's where those things came from. Most of it came from exploding massive stars. This much from dying low mass stars that threw away or puffed out some debris. This part from the Big Bang, and a little bit from white dwarfs. We'll talk about what those are. So here's what we know. The universe is expanding at an ever-increasing rate. There's only about 4.5% of all the energy in the universe is associated with the atoms that we are made of. The other 95% is mysterious. We have a flat geometry. We don't know the shape. the observable universe we have has lasted for 13.8 billion years. And the scale of the universe that we can see this is 90 billion light year number. So let me just check the time. As I said, we're gonna have a break. Oh, we have another 15 minutes. And you'll see some numbers down here. It's just page number, and I have this one there to remind me we're going to see 87 different slides today. So let's talk about the timeline of astronomy. So this chart's a little different than most. Starts in ancient times, and here's the year 1500, 16 here, and 17, and so forth. The vertical lines show the lifespan of various people. Very early primitive astronomy, other than just observing objects in the sky, real science where people wrote down numbers, comes from Tycho Brahe, who wrote down the positions of bright lights in the sky. This is before you could differentiate between planets and stars and so forth. And Tycho wrote huge volumes of data that were used by Johannes Kepler. Once Brahe had died, Kepler got a hold of his information, and Kepler produced laws for the motion of planets. Subsequently, Newton invented his law of gravity right around in here, just before 1700, and Newton was able to explain Kepler's laws. Meanwhile, I mean, there's all these other scientists who are making contributions. Here we are just past the year 2000, and here's the Hubble telescope from 1990. But let's talk about the transference or the evolution of astronomy into what we now call astrophysics. Because up until the emergence of astrophysics, astronomy was an observational art. Telescopes were invented and so forth. You see them mentioned here and there in this chart. But the reason why stars produced light was not understood until, here's observational astronomy, not until we had Einstein's relativity starting in 1905, Einstein and others creating the science of the atomic world called quantum mechanics, almost identical timescale for these. And then we had the tools to do astrophysics. Einstein showed us how light and matter move under the influence of gravity. Quantum mechanics shows what the mechanisms are for stars to produce light. And here's Einstein's theory of gravity, which is even more sophisticated than his original product. So in the early 1900s, we have the emergence of these new sciences, and that gave us the physics of astronomy, now called astrophysics. Putting all that together gives us cosmology, which really didn't start in its modern form until 100 years ago, when Edwin Hubble was not the first, but was the most meticulous in observing that distant galaxies, are moving away from us. So we have really modern cosmology, you could say, started 100 years ago with Hubble's work, but there were a lot of false starts and confusion until what we now call modern cosmology, starting in the late 1960s. Messier, French scientist, even in the late 1700s, was doing hand drawings of astronomical objects. Here's an example of one of his drawings. This is the Andromeda Nebula. He called it a nebula. Nebula kind of translates into the word cloud. We now know that Andromeda is a galaxy, and here it was as drawn by Messier in the 1780s using a telescope 4 inches in diameter in what is now downtown Paris, right near the Sorbonne. You couldn't do this today because the atmosphere is not clean enough to see as well as Messier did. And here's a photo of Andromeda. And you'll see two objects that Messier detected and drew in his artwork. This and that and that. So his drawings are remarkable because they showed structure and the relative location of galaxies and objects orbiting galaxies, either clusters or tiny little galaxies orbiting Andromeda. And Andromeda, it looks very much like our Milky Way galaxy. We can't take a picture of the Milky Way, of course, because we're inside of it. But we know the motions of the stars, and from that, we can derive the shape and the density, such as the nucleus of the galaxy has hundreds of millions of stars jammed into a small space, so that's the brightest area. So Messier actually was a pioneer in galactic astronomy in the 1780s, and each of these little pictures is a modern image from a telescope of Messier's 110 galactic drawings. So he was persistent in doing this. He just kept looking at objects through his little telescope and managing to make pencil drawings. We now have these elite photographs. Einstein, a giant in many ways in all of science, made the breakthrough in the roughly 1917 how gravity functions in the universe. At that time, the assumption was the universe was static, that it was a perennial structure. All the bright objects in the sky were in some relative position to one another, but they'd always been there. So in 1917, Einstein's theory emerged, and right away people started using his theory to try to understand how the universe would evolve. In Einstein, at that time, prior to roughly 1925, Einstein assumed, like everybody else did, that the universe was eternal and static. And he tinkered with his equations to make sure that that's what you get. However, simultaneous with Hubble, Alexander Friedman, a Russian, and Lemaitre, a priest, used Einstein's equations and explored the possibility of an expanding or contracting universe, and found that it was possible for these things to happen, that the universe could get bigger or smaller. In fact, Lemaitre had this idea if the universe, by the way, Friedman and Lemaitre knew about Hubble's work that showed that objects in the distant universe were going away from us. Lemaitre said, well, let's imagine running the clock backwards. If the universe is getting bigger, as shown by Hubble, it must have been smaller in the past. And if you look way in the past, it must have had zero size. And he was the first to conjure up the idea of what he called the primeval atom, a tiny, tiny initial something that exploded into the universe we see today. So we had the contribution of Einstein dictating how the universe might grow or decrease in size. Here's Lemaitre, who lived into the 1960s, I think, and Alexander Friedman. So I'm going to quickly show you Hubble's work. How did he do his estimate of the fact that objects were receding from us? He exploited something we're going to talk about over and over again, and that is the redshift that occurs if you have a light source moving away from you. Imagine that this is a spectrum of some element, maybe it's oxygen or hydrogen, and you do this in a laboratory. You have an electric discharge in a tube of some gas, and look at the colors that are produced. And the colors, these dark lines, are indicative of particular elements. You might call this the fingerprint of the element. Now do the same experiment looking at a distant galaxy that's moving away from us, and you will see those same lines in relative position. They're the same, but the whole thing gets shifted. And it gets shifted because the source of the light, the distant galaxy, is moving away from us. And Hubble used this fact to estimate the relationship with distance and velocity and related that to the expansion of the universe. We will do a deep dive into this in future classes. So Friedman and Lemaitre discovered that Einstein's theory of gravity allowed for an expanding or contracting universe, and that allowed for certain possibilities. Remember, Lemaitre said the whole universe might have started from a single primeval atom. And it turns out that Einstein's theory tells us if there was enough matter in the universe, that that primeval atom would grow into a universe that would ultimately collapse because gravity would overtake all of the elements in the universe and force the universe to recollapse. There are different versions of this. Another one is that the universe would get bigger and just kind of coast to gradually larger. Here's the coasting version. This is what we found. The dark energy, not predicted by Einstein, but the concept of dark energy can be put in his equations. And you get this kind of universe where the universe expands and the dark energy keeps accumulating until the influence of gravity is ignorable and the universe runs away to a increasing size. Now, from the 1930s until the late 1940s, very little progress was made on these ideas. There was not a lot of work in astronomy because of World War II and the disruption caused by European scientists fleeing from the Nazis. Observations didn't get much better. Hubble had telescopes, but the idea of the kind of modern telescope I showed you on the first page of this presentation, that was way far in the future. So observational technology kind of crept along, and there was even a drag, conceptually, there was a drag on this idea of Lemaitre's of a Big Bang beginning, because the idea of a static universe remained popular until scientific evidence showed that it could not be that way. And we'll get into that some. But all this that happened in the 30s and the 40s set the stage for the rapid progress that happened subsequently. Electronic technology, computers, understanding nuclear physics allowed us to look at the beginnings of the universe and see if nuclear theory could explain what we now observe. And we, out of this evolution of technology associated to a large degree with World War II, we got rockets and satellites and space telescopes. So this is a good point to take about a 5 or 6 minute break, and we will resume at, I have it at 1:57. Let's resume at 2:05, and we'll talk about the objects in the universe that attract our attention and how they contribute to our understanding of cosmology. So everybody's on break, and while you're doing that, let me take a quick look at the questions. And we'll talk about these when we get back. Well, greetings, everybody. We're back. And during the break, we got a couple questions. And let me just read over these two questions and a comment. First of all, Scott says, on a large scale, isn't there a law of uniformity in all directions? And what we're talking about here is something called the cosmological principle. Scott is on target with the idea, but it isn't a law, it's an assumption. In order to make progress using Einstein's theory of gravity and how it affects the expansion or contraction of the universe, it just becomes untenable unless you assume that on a large scale, say billions of light years, take a volume, billions of light years on a side, if we assume that the distribution of galaxies in that volume is uniform, then we can do the math. So it isn't a law, it's an assumption, and it's an unprovable assumption. And right now, in the field of cosmology, there's debate about the influence of non-uniform distribution of objects on large scales. And then Carolyn says something interesting. You might have, I was presenting, you might have seen the name George Gamow go by. He was a professor at the university in Boulder for quite a while, and Caroline apparently knew him and was a waitress he asked for regularly when he went to a particular restaurant. So interesting thing to know that we are among greatness, and thank you, Carolyn, for that. I'll provide more details to these questions and answers and embed them in the beginning of lecture number 2. So let's talk about objects in the universe. We're not going to talk about planets and moons and so forth. If we're going to make any progress with cosmology, we have to set aside these minuscule things like individual stars and their solar systems. But the information is there, including this drawing we will refer to occasionally that talks about the properties of stars, that namely their temperature, going from the coldest on the right to the warmest on the left, and their brightness on this scale. And we'll see the sun is right there in the evolution of stars. But we're not going to spend any time on this now. We're more interested in exotic stars like neutron stars and white dwarfs and black holes. We'll get to that. We just make a passing reference to the solar system and its surrounding cloud called the Oort cloud. There's the solar system expanded. You see the sun, Mercury, Venus, Earth, Mars, and so forth. But it's embedded in this huge cloud of icy leftovers from the formation of our solar system, thousands and thousands, maybe probably billions of chunks of ice and rock that we hope do not hit us. Here's some description of the sun. I'm not going to read it to you. All I'll say is that when we had the big eclipse in 1917 and virtually half of Colorado drove to Wyoming to watch it, or Nebraska, here's part of the moon crossing the sun and sunspots that my grandson took a picture of back in 2017. Let's highlight where we are very quickly in the galaxy. Now, I already mentioned we can't take a picture of the Milky Way because we're inside of it. But because we measure the positions of and motion of the stars and groups of stars in the Milky Way, we can draw this picture. This is an artist's rendition, and there's the sun hanging out there, not super far from the center, and about 200,000 light years across. Okay, and there's more detail here you can read if you want to. There's hundreds of billions of stars and galaxies. And Hubble was an expert at classifying galaxies. So he has this fork diagram. So you have some galaxies that have spherical shape, They're called ellipticals, that the farther over here you go, the rounder they are. And then you have these that have structure, probably as a result of collisions between galaxies. And our galaxy has this feature. It's called a barred spiral, kind of like this. You can see a straight line there. So the structural property of galaxies was started by Hubble. Here he is working on one of his telescopes, the one on Palomar. This is a particularly important drawing. This is the distribution of galaxies. Each dot here is a galaxy. This is a distribution of galaxies observed by a particular telescope system. It's called the Sloan Digital Sky Survey, I think. And you see there's structure here. Groups of clusters of galaxies all clustered together. So that this is a kind of flies in the face of that assumption about uniformity. However, this only covers 2 billion light years. At distances greater than this, the technology, the telescope and sensor technology is not sufficient to count very many galaxies. They have to be the very brightest ones. And this is our first exposure to something called Z. This is a measure of the redshift. Remember, I mentioned the redshift that can occur if you measure something in the laboratory and then look for that same element out there in the universe. You'll see a difference in where the various fingerprints of the element lie, because the distant objects are moving away or toward us. And there's a measure of that called Z, and we'll be talking about Z more as we go along. There's also a super cluster, Laniakea, flow of stars and galaxies and clusters of galaxies toward this point. And there's our location. Again, these are derived from the motion of the objects, not from a photograph. And there's a book, I think it's been republished by Alan Dressler about the Great Attractor. So here's a wonderful piece of art that appears in Wikipedia about us in a very nonlinear scale. Here's the solar system. That's the sun and Saturn and so forth, looking outward through the gas and dust of the galaxy at other galaxies, and farther out, even more galaxies, and the structure, those areas of condensation of many galaxies, looking outward toward this outer limit of our ability to see out into the universe. And we'll talk about what that is here in just a minute. So I'm not going to spend a lot of time on this. Is straightforward. Here again is Andromeda and its properties. Here's different galaxies, and the M's refer to Messier's catalog of drawings that he did in the 1780s. And if you look on the internet, you can find the Hubble Deep Field. This is the Hubble Space Telescope pointed at a spot on the sky that appeared to be empty and letting it stare there for many, many hours. And it turned out it's filled with stuff, primitive galaxies. JWST, the James Webb Space Telescope, also was asked to do this, point at a spot on the sky that seems to be empty, and look, it's dense with galaxies, and of particular interest, of particular interest is right here. That is the light from a far distant galaxy distorted by the path of light by an object between us and that distant galaxy. And we will talk about this lots. This is so-called lensing, predicted by Einstein's theory of relativity. He did not believe it would ever be detectable, and we have just slews of evidence for this kind of distortion, and it provides scientific insight. Here's some business about evolution of galaxies. Here's an even more specific computer simulation of a uniform distribution of galactic nuclei at very large distances. This is when Z is big, you're looking way back in time to the early universe, and you see that goes from 27 to 9 to 5 to 3 to 4 and so forth. And you see the computer simulations give us that same kind of structure that we saw in the Sloan Digital Sky Survey. In fact, this, when it says Z equals 0, this is the structure of galactic clusters near us right now. So there seems to be a concordance between the computer simulations we do and what we actually observe when we look at the sky, if we assume a universe that has dark matter and dark energy. Okay, so there's more detail there, and you see the ages. This is when it says 115 million years, that's since the Big Bang. And here it is now 13.8 billion years since the Big Bang. Now, we can't control everything about how we observe galaxies. This is a useful view. It just happens that nature presented M51 with a side-on view. And here it is in relation to its neighboring small galaxy. And the big one is gradually eating away at the matter in the small galaxy. Here's like a galaxy at a 45-degree angle, and here's one where we're looking at the edge. All of these have their role in developing our understanding of galactic dynamics. A particularly interesting kind of galaxy are the oldest ones, and they frequently produce this kind of effect. These are called quasars, and for decades, they were seen to be very far away and very old and stupendously bright. Gamow even wrote a little poem about, what are you guys? Why are you so bright and so old? What's the source of energy? And we now know the source of energy in quasars, which stands for quasi-stellar objects, is a supermassive black hole that's eating everything in the neighborhood. And when it collects gas and dust and stars or whatever it's in that it can eat, the disk of debris around the supermassive black hole is heated to a stupendously high temperatures, and we can see that light that was produced billions of years ago, billions of light years away. We can see it. Here's an example. We see this quasar producing a flood of light that passes through some other structure, another galaxy, and here's our telescope, in this case, the Hubble telescope, and the telescope sees this. It sees mirages, in this case, 4 of them, from that distant quasar, so bright that we can see it, even though it is now billions of, just enormous distance from us. And that light got distorted by an intervening galaxy, and we see these mirages. And that turns out also to have scientific benefit, which we will talk about. The biggest solar mass, the biggest supermassive black hole I know of right now is in the vicinity of 20 billion solar masses. That is, it's the same mass as 20 billion of our suns. And many of these objects have gone dark. So we maybe see the light, but eventually the light will disappear, because billions of years ago, there was plenty for this supermassive black hole to eat, and it ate the neighborhood. And once it eats the neighborhood, then it goes silent. It's a black hole. It's without having debris falling in, that cloud of dust and gas around it disappears, and the black hole also disappears. So something else to talk about. Here's an example where everything is lined up exactly, and we see this Einstein ring. So if you look at Einstein's equations for the propagation of light near massive objects, you see one of the solutions is Everything is symmetric, and you see a ring of light from that central object. Okay, also want to spend a little time before we get back to the science about some basic physics. Here's the electromagnetic spectrum I talked about in the first few minutes. This little slice here is expanded here into the colors that humans can see, but the electromagnetic spectrum goes towards lower energy, longer wavelengths like radio, television, microwave. All that's in the longer wavelengths. And the shorter wavelengths have light that is highly energetic, including gamma rays, X-rays, and so forth. We can only see a little slice, but we have telescopes of various kinds looking at each of these parts of the electromagnetic spectrum. In many cases, we have to go to space to see these high energy or low energy sources of electromagnetic radiation because their radiation does not pass through Earth's atmosphere. Here's a depiction of that. So if you want to do gamma rays or X-rays, you got to go to space because the atmosphere of Earth is opaque. Here's the part we can see. And fortunately, we can see clearly into the universe in radio waves because the atmosphere, our atmosphere, does not absorb strongly in that part of the spectrum. Here's that telescope complex in Chile I showed on the cover page. I actually worked on this back in the 1970s on the design of these 4 identical, stupendously large telescopes. This is a highly productive facility run by the European Southern Observatory based in Munich. You see the dormitory complex here, and they are located high in the very dry altitudes in Chile and try to stay away from urban lights and so forth. Here's the best facility we have in the US, and actually it's an international spot. This is the summit of the volcano in Hawaii known as Mauna Kea. It's over 13,000 feet. Here, my wife and I were visited there some years ago, and you see in the background 2 gigantic telescopes. Each of these domes has a 10-meter mirror, and there they are. These are funded by the Keck Foundation and various other telescopes up there. There's trouble here because of native activism about using the mountain as for science. The native peoples of Hawaii have been on a campaign for coming up on 30 years to prevent further expansion of science on Mauna Kea. And that remains a political issue. And of course, we have the Hubble Space Telescope and the James Webb Space Telescope now providing space-based information. Here's spectroscopy. This is important to understand this because of that redshift situation we talked about, where you can use you probably did this in high school or college physics, used a prism or some other technique to spread out the colors. And here's a spectrum from the sun with these dark lines indicative of certain elements in the sun that absorb spectra. So some light gets through, but there's lots of absorption. These dark lines are indicative of that. And here you see the spectrum of hydrogen and various other elements. With the more complex the structure of the atom, the more complex the absorption spectrum. And with computer technology, we can point a telescope at a galaxy and get a very large, complicated collection of spectra and then tease it apart. Now, where does this redshift come from? Even in the 1850s, the idea that the spectrum, or the colors of light from stars would be associated with their motion was understood, and we all experience it in sound by the motion of an ambulance or a train going by us and we're standing still. The approaching vehicle pitch from their siren is elevated because the source is approaching us, and then the pitch changes as soon as the object goes by. You've all experienced that. That's the acoustic Doppler shift, but the same sort of thing exists in electromagnetic spectra. And I have some examples of that. Here's the first. Here's the color spectrum that humans can see. And you see, this is a property of a galaxy. There's a spectrum of hydrogen and oxygen, these peaks. Well, you see at different Z values. Remember, Z is a measure of the Doppler shift. We have 4 examples here of Doppler shifts. So this value and this value. And you can see that spectrum is repeated in each of these examples. I have some details here. And here's what's interesting about this. If you find a nice bright source and you measure its redshift, its Z value, and you add 1 to that number, and for example, in this case, you would get a number 1.087, that tells you the size of the universe now compared to the size of the universe when this light was emitted. So let me go over that again. If you take Z and add 1, you can tell how big the universe is now compared to when the light was emitted. In this case, the universe is 9% bigger than it was when this light was emitted by whatever galaxy produced that light. That's the relative size of the universe. And this all comes from manipulating Einstein's equations of gravity. And let's give some detail to this. Back when this light was emitted, the universe was 12.5 billion years old, and the light traveled roughly 1.2 billion years. And that object is now 1.2 billion light years away from us. Here's another example with a much higher redshift. This light was emitted when the universe was only less than 10 billion years old. And that light traveled for 4 billion years. You see the sum of these two is essentially 13.8. And now this object is, since it's moving away from us, you see that it is not 1.2 billion light years from us. It's 4.7 billion light years away from us now because of the expansion of the universe. So we have this simple tool that the astronomers use. They measure the redshift, and from that you get the age of the universe when this light was emitted and the travel time and all those details. I've talked about quasars. We actually have some examples here, and you see the repeat here. This is a Z of 0.178, and you get the same spectral content here at a different redshift, and we keep going, and you can see it's here. So anytime these measurements are made, the redshift is determined, and that is a critical factor in how we tease out information. And in lecture 6, we're going to go into this in some detail, because the redshift tells us when the galaxy formed and began to produce light. So the redshift is critical. And for Hubble, the next step in analyzing redshift, because that gave us velocity, was figuring out how far away these objects are. Keep in mind, there's a difference between knowing how fast something is moving away from you or toward you and how far away it is. Those are 2 dramatically different things, and it's much easier to measure velocity of an astronomical object than it is to measure the distance. And I'll show you some history here. One of the breakthroughs in understanding how to measure the distance to distant objects was to exploit something called a Cepheid variable star. These are stars that have the property that over time they get brighter and dimmer and brighter and dimmer, and it was discovered by, she appears on the next page, it was discovered by Henrietta Leavitt that the period of oscillation, that is the brightening and dimming, is related to the distance. And so pioneering work by a woman astronomer in the early 20th century gave us this incredibly powerful technique for measuring the distance to stars. In fact, here you see a Cepheid variable star in a galaxy far, far away. M31. Again, the M refers to Messier's catalog of galaxies. Now, how do we know how far away it is? Here's the way it works. It's a so-called ladder, a cosmic ladder. You have to build a ladder in the following sense. If you've all experienced something called parallax. If you close one eye and then the other eye, distant objects appear to move. This is, remember, we all had a toy back in the 1960s that was a stereoscope or some such word, and you put a disc of little tiny photographs in it and pulled a little lever, and you would see three-dimensional representation of something. That technology that we all enjoyed as kids relied on parallax. And in fact, in the early days of astronomy, people understood that if you take a picture of the sky and wait 6 months for Earth to go halfway around the sun, the apparent position of those objects would change. And you do a little arithmetic, you can calculate how far away they are because you know the size of the orbit of Earth's orbit. And so in the early days, you could do parallax to get the distance to, for example, planets and nearby stars. But it was not until modern technology with much more sensitive instruments that you get this larger reach for parallax. And Henrietta Leavitt exploited that using photographic plates to measure these spots changing in brightness, with the period being related to the brightness. And she looked at Cepheid variable stars in small galaxies that are bound to the Milky Way. These are the large and small Magellanic Clouds. And by doing that, she was able to measure the distance to the Magellanic Clouds. And so if we click on this, you see by exploiting Earth's orbit and looking at a variable star, either a nearby star in the Milky Way or a more distant star, you can measure the distance. And so you have an army of graduate students doing this kind of work. Of course, they're all computerized systems now. The huge breakthrough that occurred is when Cepheid variable stars were found in galaxies where a particular kind of exploding star, called a type 1a supernova, occurred near a Cepheid variable star. We know the distance to the Cepheid variable star, and we use that information to calibrate the energy in the explosion that conforms to this. We will talk about this more. So now we can use supernova events, which reach out all way across the universe, to build a distance ladder, which is what we need to relate velocity and distance. Hubble attempted to do this. Oh, we already did that. Hubble attempted to do this. Here's Henrietta Leavitt. And he struggled because he did not have this technology in the 1920s. So here are the large and small Magellanic Clouds that orbit around the Milky Way. Henrietta Leavitt found this relationship between the period of the stars, the Cepheid variable stars, in the large Magellanic Cloud, LMC, and the ones nearby in the Milky Way, and you can draw a straight line through these things. There's, by the way, if you're in the southern hemisphere, you can see the large and small Magellanic Clouds and the disk of the Milky Way. So lots of effort was required. Now, let's take a look at galaxies. We look in different wavelengths. Here's how a M51, I think this is, in the radio spectrum, the infrared spectrum, optical, ultraviolet, and X-rays. So there's stars and gaseous regions in that galaxy that are pumping out X-rays. These are star-forming regions, highly energetic. Over here in the radio spectrum, you're looking at cool, low energy radiation. even looking out into the Milky Way, we can see differences in radio, infrared, optical, and X-rays, looking into the disk of the Milky Way, even gamma rays coming from places in the Milky Way. Okay, so now we've gone through that. Let's go back to the science. This idea that the universe is expanding, I already explained. Einstein tried to match his equations to the concept that was prominent at the time, that the whole universe was static. It had always been in the form and distribution that it was at that time. Nobody expected anything different. So here we go back to the comment made during the break from Scott, that there's a cosmological principle, and it says that on a large scale, the distribution of energy, matter, and position of galaxies is the same everywhere. And as far as we know, on large scales, that's true. Remember, we're talking about a universe which is essentially 45 billion light years in radius. So if you take big chunks like area 5 billion light years on a side or something, you see the same number of galaxies and a uniform distribution. It's another part of this principle is that it doesn't matter which direction you look. Everything is the same, no matter which direction you look. And we don't occupy a special place. We are certainly not the center of the universe. And all observers, even the ones far, far away from us, will have this experience with the average density of galaxies that surround them. But all observers have a different observational universe. So these are features of the cosmological principle. And this is the model that is most in favor right now. Could change, but we're going from left to right. We're going from early time to the current time. That there was some kind of quantum event, unexplained as yet, that led to the birth of our universe. This is the primeval atom that Lemaitre was talking about. And we have an idea we'll talk about some weeks in the future about a period of inflation that led to the current expansion of the universe. But there's this really interesting history that we now understand. In the early days, up till about 375,000 years after this emergence of our observable universe, there were no atoms. The energy levels, the intensity of the light in the early universe was so stupendous that if a proton and an electron decided to get married and found each other, inevitably a high energy chunk of light we call a photon would have come along and knocked them apart. So it's just a soup of high energy subatomic particles swarming around, banging into each other until the universe had expanded enough for atoms to form. That happened 375,000 years, roughly, after the Big Bang. Now we have a dark universe. There are no light sources in the universe, and it stays dark for 400 million years. Just gas and dust floating around, and we don't get stars until around this time. Now, this piece of artwork was drawn 15 years ago, and we now have new information from James Webb that suggests this 400 is probably more like 220 million years. But keep in mind, the universe stayed like a soup of particles for 400,000 years and then was totally dark for hundreds of millions of years until stars formed. And then we had light sources. And those stars acted under the influence of gravity and stars found each other, and eventually you get galaxies. That's all a galaxy is, of course, is a collection of hundreds of millions or billions of stars. But we have this very interesting period called the Dark Ages. Another interesting thing about this interval is when there were no atoms, it was just light flying around in the universe. The universe became transparent at this time. So that light produced prior to this time now could flow freely, and we still can detect it. And we see this, it's called the cosmic microwave background. It was predicted in the late 1940s, not detected for another 20 years, and now we have detailed information about the cosmic microwave background, this disk of yellow and red and blue. But we'll go into that in more detail. But that light is still flowing in the universe, and we have pictures of it. That's extremely useful. Tons of information. And then we just have evolution of galaxies and solar systems and planets. And you see the curvature, the artist drew this with a little upward curvature. That's supposed to indicate the influence of dark energy that I showed you emerged about 7.5 billion years after the emergence of our universe. Okay. Now let's talk about what Hubble was able to discern when he looked out into the galaxies, out into the universe, and saw galaxies moving away from us. As far as I can tell, I've read some history of astronomy in the 20th century. As far as I can tell, Hubble did not know that much about Einstein's theory of relativity. He presumed that the reason we saw galaxies receding from us is similar to the following concept. Imagine you go stand by a lake and you see a boat go by. He assumed that the boat standing in for a galaxy was propelled by some source, and the galaxy was moving away from us through the space, a static space that was eternal. But there's another way you see this possible motion of an object. Imagine instead of being a lake, this is a river. And a boat goes by, the boat can be moving because the water's flowing in the river. And we now understand, in a way that Hubble did not, that the galaxies are moving away from us because the space between the galaxies is getting bigger. That's the expansion of the universe we've been talking about. And the expansion carries those galaxies away from us, even if they are not moving in the space in which they are embedded. Both effects can produce a redshift. Remember, all we have to say about galaxy motion is redshift. So Hubble probably died, he died in the 1950s, I think. He probably died before realizing that it was the expansion of the universe that's carrying the galaxies away, not velocity of the galaxies in the space in which we are embedded. So here's some language you can read. We now think that's not the case. And by the way, if you're interested in seeing a humorous version of this, you can click here and watch about 3 minutes of the movie Annie Hall, in which Woody Allen correctly depicts what's going on here. The mother takes her son to the doctor because this kid has stopped doing his homework because he's learned that the universe is expanding. And what's the point? The whole universe is going to explode or something. And he has a brief chat with the doctor, who spends the whole time smoking a cigarette, by the way. I encourage you to read that or watch that. It's very humorous, but it's technically correct. So what we have, we're going to go back to our balloon analogy, which is the best thing we have for talking about this, that in the early days of the universe, the early galaxies were closer together. And as the universe has expanded, the space between the galaxies has gotten bigger. And we have this analogy with the ants walking around on the surface of their two-dimensional universe. We are not in a two-dimensional universe. We're in a three-dimensional universe, but perhaps this kind of analogy gives us some comfort when we talk about what it means for the universe to expand. That is, the distance between objects, in this case, the ants, the distance gets bigger even if they're not moving. Not because they're moving, they're crawling around. It's because the distance along this measure here is getting bigger because the size of this universe that they live in is getting bigger. Now, here's Hubble's original data from 1924-25. And by the way, I hope you appreciate the interesting timing of all this. Einstein's theory of gravity, which explains expansion of the universe, was produced in full form in 1917. Hubble was just starting to measure the motion of galaxies at that time, and by 1925, he had a catalog of particular objects. These dots represent distance, the best he could estimate, and velocity. Each one of these was a galaxy. That we would not have understood what was going on here, except that Einstein's theory and Hubble's work were almost simultaneous. So just a happy accident. Now, over the years, we've learned that Hubble's initial estimates were way out of line because his ability to measure the distance to these objects was limited by the technology that existed in the 1920s. The cosmic ladder was primitive, and he was getting numbers for the expansion rate way up here. And over the next 100 years, we have gradually made it better and better and better. And right now, 10 years ago, we had a number that's here. And so we've made great progress in getting the expansion rate in a way that Hubble tried to do with limited ability. The actual line that he should have gotten was this one. But all is not well in the world of Hubble. We have a thing called the Hubble constant, which is what we calculate from the slope of this curve. And we have different methods for measuring the Hubble constant. And frankly, it's a mess. Up until about 2012, the measurement technique using Cepheid variable stars that were discovered in the 1920s, and that cosmic microwave background also gives us a measure of the expansion rate. Everything was fine because the error bars on the Cepheid variables and the error bars on the cosmic microwave background, this darker stuff, they overlapped and everybody was pretty content up until 2012, 2014. But as the methodologies improved, we discovered that the Cepheid variables predict an expansion rate here, and the cosmic microwave background predicts an expansion rate here, and it's not even close. See, we have this, and this problem continues. This chart stops here. We are in 2025 now, and this problem has not gone away. A recent entry into the effort to clear up why we can't get the same measurement from two different methods for the expansion rate was a proposal called TGRB. We don't have to go into what it is. And data was collected and it came out right in the middle, which just, it doesn't help. So this is now called the Hubble tension, meaning why can't we get different techniques for measuring the expansion rate of the universe to agree? And it's the hottest topic in cosmology right now. The James Webb Space Telescope is here. And here's the dilemma. the telescopes measure what they can see looking at distant galaxies. So they're looking at individual galaxies and making data collection of individual galaxies. The cosmic microwave background is presumably a better technique because this light is the oldest light in the universe. Excuse me for going backwards for a second. I don't like doing this, but I want to. This oldest light from 400,000 years after the Big Bang, that light has propagated through the entire universe and its entire age to get to us. That should be a better measure of what the universe is doing because it sampled all of the space and time the universe has existed. But it doesn't agree with the Cepheid variable technique. And that remains a big problem. So there's some more information here. It's this gap that we're just won't go away, and it relates to the age of the universe. If you take that Hubble constant that I talked about and take its inverse, like 1 over the Hubble constant, that's the age of the universe. And so we have about a 10% misunderstanding about the age of the universe. Everybody still talks about the universe being 13.8 billion years since the Big Bang, but now it's plus or minus 10%, and we're not happy with that. Now, here's the good news. Here's data from comparing the James Webb Space Telescope in red dots and the same data taken by the Hubble in gray dots. And you see the red dot, the cloud of data, is a little tighter. It's more compact. The spread is smaller. But still, it's a major problem and could be a huge embarrassment because the fact that the universe is expanding at an expanding rate won a Nobel Prize. It would be a shame to discover that that work was somehow incorrect. So it's a big problem. The Hubble tension, we'll talk about it many times. Here's the Big Bang. We've already seen this chart. Now, this is further confirmation that the universe contains only about 5% of its energy is in atoms. These are models of how the emergence of different atomic types, helium, isotope of helium, lithium, and something called deuterium, how they would appear as a function of how much of the universe is atomic matter versus some other kind of matter. And when you do that arithmetic using the models of nuclear physics that emerged from World War II, this is the best spot to be for the universe to agree. And what I mean by agree is, see this green line is measurement of deuterium in galaxies. This is the prediction of the model, and they agree, but only if about 5% of the universe is atomic matter. But that's what we got from other methods. So we have confirmation from the early universe, emergence of different kinds of atomic material. Here's the cosmic microwave background I've talked about a few times. We're getting near the end of the lecture, but I want to point out, this is a picture of that oldest light. Remember, I pointed out it was yellow and red and blue. This is, imagine you're out in space looking around you. There's a sphere around you, and it has this ancient cosmic light operating at the same wavelength as your microwave oven at home. And it's drawn in this way for some scientific reasons. But the idea is, if I put you out in space in a spacesuit and said, draw everything you see in the sphere around you, you could look up, that's what this one represents, or you could look down, and then you could rotate around your waist. So this would be 180 degrees, this would be 360 degrees from here to here. And if you took photographs in the wavelengths of the electromagnetic spectrum consistent with your microwave oven, this is what you would get. The interesting thing, and they're different temperatures. The red is warmer, the blue or black is colder. But the interesting thing is the temperature variation across the sky at this wavelength is ultra tiny, 5 parts in 10,000. So the universe is extremely uniform, but not exactly uniform. And that deviation from exactly having the same temperature everywhere from the oldest light in the universe is filled with information that we will be talking about. Remember, it comes from the time when the universe became transparent, 380,000 years after the beginning of our universe. So this is the entire sky. This is 180 degrees, and this point and this point are the same point, because if you spin around, that allows you to cover the whole universe. Now, do we have any confidence in what we're doing? And this is the most important thing I can show you today. We have about 5 minutes to talk about concordance. This is what I call the carrot and the celery drawing. If we use various measures, supernova events that relates to Cepheid variables as a technique, something called baryon acoustic oscillations, here's the cosmic microwave background, and let's use these to find the most likely place where there's an intersection between the amount of the universe that is matter and the amount of the universe that is dark energy. That's a Greek letter, lambda, and that's universally used as a symbol for dark energy. And you can see this acoustic oscillation thing is kind of fuzzy with respect to how much matter is in the universe, and even worse, how much what. So we put that on the chart, and then we add the microwave background and the supernova, and they all intersect here. So we have some reason to believe that the center of this ellipse is an important spot in determining how much matter and dark energy are in the universe. Let's zoom in on that and add some additional information from the lensing. Remember, Einstein predicted that light propagating through the universe would be affected by massive objects like galaxies. That's what lensing means. That further confines the intersection point of all this data. And I've zoomed in here, and this orange ellipse and this orange ellipse are the same orange ellipse. So we now have at the center of that ellipse, it's the most probable place. And it turns out, if you look at the center of this, that the matter in the universe is at about 30%. There's 32, there's 24. Right there, about 30% matter and 70% dark energy. And that's exactly what we observe. So I'm going to conclude with this. Here's the pie chart I showed in the beginning. 70% dark energy, 25% dark matter, and there's other kinds of matter. So this adds up to 30. Now let's look at actual measurements of galaxies. It doesn't matter how we've laid this out or what it represents, but these are measurements with error bars on galaxies. If we take the numbers we get from the concordance, or these two numbers, and we put them into Einstein's theory, this dark green line is the 30%, 70% partition between matter and dark energy, and it matches very well with the observations. If you choose other partitions of matter and dark energy in the universe, you don't get anywhere near the right answer. So this gives us high level confidence that the universe is 30% matter, including dark matter, and 70% dark energy. And it seems like we understand what we're doing. But I'm not going to go through the summary. There's the Hubble tension. Unexplained. We got to work this problem. And here's a picture of the distribution of dark matter teased out by looking at how light propagates near galaxies. It's big clouds of stuff. We don't know what it is. And dark energy, I would like to draw a picture, but I don't even know how to draw a picture of it. It's just a property of the universe that's not understood. So this is the pie chart. We'll go into this in more detail. I'm going to stop at this point because it's 3 o'clock. Thank you for your attention. I see we have more questions. I'm going to capture all these questions and I will have answers by the time we start lecture number 2 next week. And I will see you next week for more fun. Thank you.
You got all the questions, Ed?
Let me check. Let me check real quick. I just grabbed. Uh, hang on. Don't. Yes, I have all the questions.
Wonderful. I will see you next week.
Yes, thank you.